What's up, guys? It's Mr. Bringle, and today we're going to be going through the second practice for drawing free body diagrams. So, on this first problem, same as before, we are going to be drawing the free body diagram for the object that's underlined in the description here, in this case, the bird, the pirate bird. And it says a bird sits motionless on a perch. So we know that gravity pushes down on the bird, but the bird is not falling through the perch. So there must be an oppositional force, something to balance it out here because the bird is not moving. So at the very least, I know these two forces are balanced. Now, the upward force would be a contact force between the bird and the perch that it is sitting on. And it is a reaction to the bird pushing down on the perch, and that is a normal force. Okay. There are no horizontal forces acting on the bird here, nothing pushing it or pulling it left or right, so we are good to move on here. Increasing the difficulty a little bit here, this one is a little bit tricky. It says a hockey puck has already been hit, and it is now sliding on its own across frictionless ice. So purely frictionless ice probably doesn't exist in real life, but for the purposes of this, let's imagine there's no friction. So if I hit the hockey puck with my hockey stick, and then let's say it leaves my hockey stick at 5 meters per second, we need to think about how would the velocity of the puck continue on after that point if there is no friction and I'm no longer in contact with the puck. So sit on that for a second while we think about the vertical forces acting on the puck here. So in this particular case, we are going to have gravity pushing down on the puck as usual. And I know the puck's not plummeting through the ice, so there must be an upward force that is balancing the force of gravity there. That is going to be the normal force, the reactionary force pushing back up on the puck from the contact surface, in this case, the ice. Okay. Now, horizontal forces here. We said that the puck would go across the ice after it's been hit and it's frictionless ice. So that means there's no friction slowing the puck down. I'm also no longer pushing the puck with my stick. It's just on its own. So in this case, the puck is actually just going to continue on at a constant velocity because there is nothing to speed it up or slow it down. So this would be similar to throwing an object in outer space. Once you throw that object, it is going to continue on in a straight line until an unbalanced force acts on it. So this is basically a demonstration of Newton's first law, the law of inertia. And that one can be a little hard to understand. If friction was present here, so if it was ice and there was a small amount of friction, assuming this puck was moving, let's say, to the left, you would draw an arrow to the right for friction, and that would be it. Eventually, that puck would slow down and stop. Moving on to our next page here. This one, we have a baseball player that has already jumped and is now sliding across the ground to reach the base. So we are specifically talking about this guy right here, and he is sliding this direction to the left to get to the base. Now, this is after he's jumped. So he did have to apply a force initially to push off the ground. However, this is once he hits the ground and is just sliding on his own. Okay, and we put here, make sure to think about what would happen to the player's velocity as he slides across the ground. Okay, so as always, we will include the force of gravity acting on the player here, and because the player is not falling through the ground, there must be something balancing that out. That is, once again, going to be the normal force because the player is in contact with the ground, the dirt, and that is going to support him push back up. It is the reaction to his downward push on the ground. Now, assuming this player is moving to the left here, once the player is sliding, there is no active force pushing or pulling on the player to get them to continue to slide to the left. There is no applied force. to the left. However, what we are going to have, since they're sliding across rough ground, we are going to have a rightward force of friction. Now, what we've drawn here is unbalanced forces in the horizontal direction, meaning there is a force to the right and there is no force to the left, which will cause the baseball player to accelerate. And in this particular case, it is going to slow the baseball player down and he will come to a stop, which hopefully makes sense. Moving on, a football has already been thrown and is now traveling through the air. So this is after it's been thrown, and it's just flying through the air here. In this particular case, we are going to have gravity pushing down on that football, and that is it. And the reason for that is because I applied the force initially to throw the football, but once my hand is no longer in contact with that football, I'm no longer applying a force. I have to be in contact with it to apply the force. There's no normal force here because it's not in contact with the surface. There is air resistance would be present. Of course, that would be in this case probably multiple directions depending on the trajectory of the football. But in the case of neglecting air resistance, as we do a lot, then it would just be gravity acting on the football. Gravity will always point directly down. Last one here would be our bucket that is getting pulled up from a wall at a constant speed with a rope. Okay, so as always, FG points down, and because it's moving at a constant speed, I do know that my forces are balanced in the vertical plane here. So I will have another upward force. These will be balanced. However, this one is unlike our previous examples where the normal force balances out the weight of the objects. In this case, the tension in the rope is what's actually supporting the weight of the bucket here. So this will be labeled F subscript T. And for there to be a normal force for this bucket, there would have to be something underneath it that's supporting it, preventing it from falling down. But again, in this case, the reason the bucket does not fall down is because the tension in the rope is pulling up on that bucket. So this concludes practice set number 2 of your free body diagrams. And we will have more practice in the future.